Good afternoon, everyone. My name is Himanshu Nagpal, Assistant Professor in AKGEC. Today we'll discuss about the one of the optical source used in the optical fiber communication, that is the LED, and we will discuss about the today we'll discuss about the basic principle of LED, or you can say small basic principle of LED, and mainly we'll discuss about the quantum efficiency, internal quantum efficiency of LED, external power efficiency of LED, and the coupling efficiency of LED. So first we'll talk about the LED. This LED is the one of the optical source or active component in the optical fiber communication. Its fundamental principle is to convert the electrical energy in the form of a current into a optical energy, means electrical energy which is in the form of current and which carries the signal is converted into the optical energy in an efficient manner, and which this allows the light output to be effectively launched or coupled into the optical fiber cable. Let's say if I say this is a input signal, and this input signal in the form of current, clear, and this and then the LED is there which produce the optical light or light signal, and this further which optical fiber is connected. This light output is directly entered into the optical fiber cable, clear, in an efficient manner. So major requirements for an optical fiber ammeter, that is the major requirement for the good optical source, that a size and configuration should be compatible with the launching light into an optical fiber cable, means the light output should be highly directional and must accurately track the electrical input signal to minimize the distortion and noise. Means if the input is vary, the output signal should also vary linearly. So this the source should be linear, should emit the light at wavelength where the fiber has low losses and low dispersion. Means the optical source should be should produce a light which is at that wavelength where the fiber has a low losses and low dispersion. This preferably we will always talk about that optical source which requires a simple signal modulation. So we always prefer to have optical source which can be used for the simple signal modulation over a wide bandwidth. This optical source must couple sufficient optical power into the optical fiber cable, so the optical source should have a higher coupling efficiency as compared to the previous one, clear. And this optical source should have a narrow spectral bandwidth, or you can say narrow spectral line width, in order to minimize the dispersion in the fiber. These are the major requirements of an optical fiber of an optical source. And next requirement is it should not be sensitive to temperature, means the output should be stable and should be unaffected by the change in the ambient conditions like temperature. Temperature means temperature sensitive should be very low, and the source is optical source should be comparatively cheaper and highly reliable in order to compete with the conventional transmission techniques. Means the optical source should be reliable and should be easily compatible with the latest techniques of used at the transmission side. Now this LED source, basic principle of LED source is the spontaneous emission. Basic principle of LED is the spontaneous emission, and you can say in the LED, let's say this is a LED, and this LED shows like this one. When the LED is provided in the forward direction, then the current will produce, then the optical light energy will be produced. So this PN junction should have a PN and N area, and there will be a depletion area where the depletion region where the recombination take place and photon will be produced after recombination. Clear? So basic principle of LED is the spontaneous emission. You can see here that, let's say this is a valence band and this one is the conduction band. When we are providing the energy, the valence electrons at the valence band, electron or you can say any carrier move to electrons at the valence band will move towards the higher energy state, and that is a conduction band. This process is known as the absorption because it absorbs the energy, and this by absorbing the energy, this electron gets excited and moves to the higher energy level, that is E2 minus, that is E2, and this energy should be greater than the E2 minus E1. So the after absorption, the electron get excited into the conduction band. Now after around 10 to the power minus 9 second or 10 to the power minus 8 second, this electron automatically comes back into its original position to get the stability. So when it come back to its original position means original band, that is when the electron comes back into the valence band as where it was previously at a conduction band. So when it gets into the valence band, it jumps back into the valence band, it produces a photon. Photon will be produced. So this is the basic principle of LED, working principle of LED. So we will mainly talk about the LED power and efficiency. Now see, we will talk about the LED efficiency in terms of internal quantum efficiency, external quantum efficiency, external power efficiency, and we will discuss about the coupling efficiency. Clear? So first we will talk about the internal quantum efficiency. So internal quantum efficiency is defined as the number of photons generated internally, number of internally photons generated to the number of electrons supplied into the device. Clear? So this internal quantum efficiency is ratio of photons generated to the injected electrons. As we know that this is the LED and we are providing the current. So when we are providing the current, it means we are injecting the current into the PN junction diode, which is a LED. So the power internally generated by the LED can be determined by the excess electrons and holes in p-type and the n-type material. So as it contains the majority carriers are photons and holes in their p and the n-type material, and when we providing the forward biasing means we are also injecting the electrons into the device. So excess density of electrons, that is delta n. Let's say initially excess density when it is in the, when when the no current is provided into the optical into the LED, the excess density of electrons delta n, initially there are electrons, that is delta n, and the delta b, number of holes in the initially, is equal, since the injected carriers are created and recombined in such a way that the charge neutrality is maintained within a structure. Initially when there is no current supply, the charge neutrality will be there, and the number of excess electrons will be equal to the number of holes. So when we are providing the doping in extrinsic material, one carrier type will have a higher concentration as compared to the another type. Okay, so hole concentration will be much greater than the electron concentration in the p type region. So this, due to recombination, the electron density, the excess carrier density decays exponentially with time. As the recombination takes place, the electron density, excess electron density will be decay exponentially with time, and that is given by the delta n is equal to delta n naught exponential minus t by tau, and this delta naught is the initial electron density delta n naught is the initial injected electron density, and T represents the this tau, this is tau, this tau represents the total carrier lifetime. Clear? So and where delta n is only a small fraction of the electrons which are left after recombinations. So as recombination takes place between the between the holes and the electron density gets decreases, and this expression is decreases in an exponential manner, and this delta n is the number of electrons remains after certain time, that is delta n is equal to delta n naught exponential minus t by tau. Now see, when there is a constant current flow into the junction, the equilibrium condition will be maintained. When there is a constant current in the current flow into the junction diode, the equilibrium condition will be maintained. So total rate at which the carriers are generated will be equal to the sum of the externally supplied electrons and the thermal generation rates. Means the rate at which we are providing the electrons. Clear? The rate at which the electrons gets left should be equal to the number of electrons we are supplying in a particular time, or in a second, minus में number of photons generated, or you can say the thermal generation rate per second. No, you can say minus में number of thermal generation. Thermal generation means the photons will be generated, non-radiative components and radiative components both will be there. So means the electrons which are left, let's say if I say we are providing a 20 electrons per second into the device. So these 20 electrons gets recombined, and then after 1 second, let's say if after 1 second 14 electrons will be there, will be left. That defines the rate d delta n by dt. The rate at which the electrons decays with respect to time is equal to the number of electrons we have supplied minus में number of electrons which gets lost in the form of heat, or you can say number of photons generated, and this number of recombinations that includes the radiative and the non-radiative. Clear? So d delta n by dt is equal to j by ed minus में delta n by tau. Clear? So this j by ed is the electrons injected per cubic meter per second, and d is the thickness of the recombination region. Clear? And this delta n by tau is the thermal generation rate, means the electron which gets depleted due to the heating effect, that is given by this one. Now at this equilibrium condition, this rate, the number of electrons we are injected should get equal to the number of photons generated, or you can say number of electrons get radiative combination, non-radiative combination, that is J by ED will become equal to delta n by tau. So delta n will become equal to J into my tau divided by ED. Clear? Now see, in a steady state condition, the total number of carrier recombination per second will be equal to, means if I say, when I have told you this is equal to what? Total number of electrons get depleted due to the recombination. Clear? And this include the radiative recombination and non-radiative recombination. So I can say that if I say this is a total recombinations per second is equal to J by ED, and this radiative recombinations will be equal to sum of the radiative recombinations plus with non-radiative recombination. Non-radiative means if I say P and junctions, electrons and holes get recombined, there will be two cases. In one case, photon will be generated, that type is known as the radiative recombination, and another case when photon will not be generated, but heat is produced, means electrons get after recombination only thermal heat will be produced. So that type of known as the non-radiative recombination. Clear? So this total recombinations will be equal to RR plus में NR. This is radiative recombinations plus में non-radiative recombinations per unit volume and per unit per second. So when the forward biasing current is provided, the total number of recombinations can also be written as total number of recombinations can also be written as the number of the current supplied divided by the electron charge. This RT will become equal to I by E. The total internal quantum efficiency can be written is equal to the ratio of the radiative recombination divided by the total recombinations, or you can say this is equal to radiative recombinations divided by radiative recombinations plus with non-radiative recombination, because radiative recombination produce the photons and total recombinations produces the photons plus by heat, and in both the cases electron will get depleted. So this internal quantum efficiency equal to RR upon by RT is equal to RR plus में RNR, and this can also be written as radiative recombinations per second and divided by the total recombinations per second. Clear? So, and this is also, we know that, and from the above equation we know that the RT is equal to what? I by E. So we can see that the RR is equal to internal quantum efficiency multiply में RT, and this is equal to I by E. Clear? So this is RR is equal to internal quantum efficiency multiply में I by E. So now, as I already told you, the number of recombinations per second, that means the number of photons will be generated. So total power of photon, total number of power generated by the LED, that is represented by P internal, will be is equal to what? Energy of number of photons generated per second. Clear? This is number of photons generated per second, or you can say radiative recombinations per second. Then this is equal to RT multiply में energy of one photon. This is a simple case. If I say one pen cost 10 rupees and we have to you have 10 pens, so how much money will be spent on purchasing the pen? So we will 10 multiply with 10 rupees. So here say if the total power generated by the LED means number of photons generated by the LED is when it is multiplied the energy of one photon, you will get the total power. As we know that the energy, this RT is equal to internal quantum efficiency multiply में I by E, energy of one photon is equal to h nu. So this one P internal generated is equal to internal quantum efficiency multiply I by E into में HF, and this F equal to C by lambda. So this one is the total power generated by the power internally generated by the LED. Clear? So internal quantum efficiency can also be defined in terms of carrier lifetime, and this internal quantum efficiency is can also be equal to the, as we know that internal quantum efficiency equal to this one. So you can also see that total recombination lifetime, this is what per second now. If I talk about the internal quantum efficiency in terms of time lifetime, so this RT, this RR can be written as 1 by tau R, and this RT can be written as 1 by tau T. So this is tau divided by tau R, can also be defined, internal quantum efficiency can also be defined in terms of these carrier lifetime. So you can see here that this can also be written as RR upon में RR plus में RR NR. So you can see that it can also be written, if I divide the RR by both sides, 1 plus में R NR upon में RR, and this can also be written as 1 upon में 1 plus में tau R divided by tau NR. Clear? So the internal quantum efficiency can also be written as 1 plus में 1 by tau R upon में tau NR, and total carrier lifetime is equal to the, as we know that this RT is equal to RR plus में RNR. Now when I talk about the in terms of carrier lifetime, this is equal to 1 upon में tau is equal to 1 upon में tau R plus में 1 upon में tau NR. Clear? So this total internal quantum efficiency can also be written as tau by tau R, which I already told you. So now the next is the external quantum efficiency. So external quantum efficiency is equal to the sum, one of the factor K should be multiply the internal quantum efficiency. Clear? So external quantum efficiency can be defined as the ratio of the photons generated emitted from the device when the LED electrons light photons generated internally, when it is get emitted from the device, that the photon emitted from the device to the total number of photons generated. Sometimes it can also be written as, can also be defined as the ratio of the number of photons generated emitted to the total number of carrier recombinations, means radiative plus में non-radiative. Clear? So so external power efficiency is equal to the external power emitted from the device divided by the total power supplied, electric power provided to the device multiply में 100. This is the external power efficiency, PE divided by P multiply में 100. Clear? Now this PE, external power which is emitted from the device, is dependent upon the internal power generated multiply by some factor, because this PE should be less than the P internal. This is factor, this depends upon the transmission factor. Means if I say this is a LED surface and it gets fabricated by this glass surface, glass covered by the glass, so total number of photons generated emitted from the device, that defines the external quantum efficiency. So, or you can say external power efficiency. This PE is equal to total power internally generated by this device multiply में some factor, and this F is what? F is the transmission factor of the glass, multiply में N is the refractive index of the material by which it is made. Sorry, and N is the refractive index of this material, this area. ठीक है, multiply में 4 into में n square x, and this nx is the refractive index of the material by which LED is made. So now next one is so in the next class we will discuss about the coupling efficiency, and we will discuss about the coupling efficiency. Clear? Thank you.